What's up, everybody? Hope you're all doing well today. We're going to be looking at simple harmonic motion. I'm going to be going through a bunch of problems from your review sheet. So I'll link to the review sheet if you want to try them in advance. Otherwise, let's go ahead and get started. All right, let's look at this question. We are going to have a spring here, and we're going to hang a mass from the spring. We're going to hang a 500 gram mass. When we do that, the spring's going to extend here a certain distance, in this case 22 centimeters. And then we're going to calculate a few things. So for example, let's find the spring constant. So when this drops down, the reason it drops down is because gravity is pulling it down. So there's going to be a force of gravity pulling down here, mg. And then the spring, the farther it pulls down, the more the spring's going to pull back. When we're in equilibrium, then those two forces are going to be equal. So the force of the spring is going to be equal to the force of gravity. So we know the equation, Hooke's law, is going to be kx. We know the force of gravity is going to be mg. So from here, we can just substitute in everything we know and solve for k. So k is 22 centimeters. We'll go ahead and convert that to meters. And then our mass was 500 grams. Actually, let's convert that. So it should be 0.50 kilograms. And then we'll just multiply by 9.8. Okay, solve for k. When you solve it, you get 22.3 newtons per meter. All right, so letter B now is saying, okay, now our mass, it's going to start oscillating in simple harmonic motion. So it's going to start oscillating back and forth, and we want to know the period. So the equation for that is t equals 2 pi square root of m over k. And then, we'll just solve it, so it's not too bad. So square root of 0.500, then we'll just substitute in the k that we just solved, 22.3. And then we just solve that, we get a time of 0.941 seconds. Easy enough. The frequency now, so the relationship between frequency and period, remember, period, you can think of this as seconds per cycle, and the frequency is cycles per second. So these are just reciprocals of each other. So letter C then, F is equal to 1 over t. So we'll simply go 1 over 0.941 seconds. Okay, and then we get 1.06 cycles per second, which is also known as a hertz. All right, let's move on to the next one. All right, so we have a pendulum. And our pendulum is going to be oscillating back and forth, okay, with a period of 2 seconds. And we're just simply solving for the length of string. So what is the length going to be for this to happen? So t equals 2 pi. This is the equation for a pendulum, L over G. And we'll just go ahead and sub in the numbers, 2 pi square root L over 9.8, and the t was 2. Okay, why don't we go ahead and do the algebra here? So we're going to go 2, let's divide by 2 pi. Okay, so that gives us 1 over pi equals L over 9.8 square rooted. And then we'll just go ahead and square both sides, right? Square this. So we get 1 over pi squared equals L over 9.8, or L equals 9.8 divided by pi squared. Plug it in the calculator, and we get 0.993 meters. Easy enough. Let's look at the next one. All right, so for this question, we have our spring and our mass. And this is going to be oscillating in simple harmonic motion. Okay, let's go ahead and draw this out. So we have a 4 kilogram mass. The amplitude here is 8 centimeters. Remember, the amplitude is from this kind of equilibrium point to like this x max position here. And then we are given the spring constant. This is going to be 120 newtons per meter. So we're solving for several things: potential max, kinetic max, velocity max, and acceleration max. So the first thing, it's probably the easiest one, is just going to be the US maximum. So that's just 1/2 kx squared. So plug them in. We got 1/2 times 120 times the x, which is our 8 centimeters, so 0.08. Square it out, and we get 0.384 joules. So that's our US maximum. Now remember, US max, that would be located, let me change my color here, that would be located about right here at this peak. And then as it's moving back this way, it's going to change into a K kinetic energy. So as long as there's no friction, then US max should equal KE max. So KE max is also going to be 0.384 joules. Okay. Well, velocity max, remember kinetic is directly related to velocity, so the equation for kinetic is 1/2 mv squared. So we know that the maximum kinetic is 384 joules, 1/2. The mass in this case was 4 kilograms times v squared. So we go ahead and simplify a little bit, divide by 2. So 0.384 divided by 2 equals v squared. And then we'll go ahead and square root that out. So this should be square root of 0.384 divided by 2. When you do that, you get 0.438 meters per second. All right, final question now. We're looking for the acceleration maximum. By the way, velocity max and kinetic energy max should be at the same place. And the acceleration max, that would be right here, right at the peak. Notice as you start pulling it back more and more and more, the force of the spring is going to get bigger and bigger and bigger, and therefore the acceleration is going to get bigger. So A max would occur when F is a maximum. So remember, F max is coming from the spring, so the equation for that is Kx equals ma. So we'll just go ahead and sub in everything. So we got 120, x was 0.08, and then our mass was 4. So multiply 120 times 0.08 divided by 4, and that gets us 2.4 meters per second squared. All right, let's move on to the next one. All right, so again, we have another mass. This time it is has a period, so it's kind of like the last problem, but it's giving us different things, right? So this tells us that it's oscillating back and forth again. This time they give us the period, so t equals 4 seconds. The mass is 2 kilograms, and they're saying V max is going to be 0.6 meters per second. So the first thing we do want to find is the spring constant. Okay, so we will use, in this case, we'll use this equation. Since we know the period and we know the mass, we should be able to find the spring constant. So we have 4 seconds equals 2 pi square root of m over k. The m in this case is 2, k is here. So I'm going to go ahead and do the algebra here. I know some of you sometimes have trouble with it. So we'll divide by 2 pi, and that's equal to the square root of 2 over k. And then what you're going to want to do is square both sides. Actually, if you want to keep it easy, go ahead and do the math on this first. So when you divide this, you get 0.637. And that equals square root of 2 over k. Then you can square both sides. So when we square those, let me go finish it up here. When you square those out, you get 0.405 equals 2 over k. Then we'll kind of cross multiply here, so k equals 2 divided by 0.405. So when you divide 2 by 0.405, you get 4.93 for k. And again, that's newtons per meter. All right, let's go ahead and find the frequency. Actually, let's make some more space here. So we're going to find the frequency. Remember, the frequency is simply the inverse, the reciprocal of the period. So the period in this case was 4 seconds, right? So that's easy. Frequency is 1/4, or 0.25 hertz. So that's letter B. Letter C, what is the amplitude? So we're looking for that maximum displacement here. So to do that, we're going to use the maximum velocity. So remember, V max was 0.6 meters per second. So now we can easily calculate kinetic energy max. Kinetic energy max would just be 1/2 mv squared, right? So if we do that, 1/2, the mass was 2, and then we'll go v squared, so that's 0.6 squared. So that cancels. So it's basically just 0.6 squared. So 0.6 squared gives us 0.36 joules. So that's our kinetic energy max. Well, that would happen right here. So to find the x max, the amplitude, we know that's when us is also going to be a max. Remember, wherever kx is a max, then at the opposite extreme, us will also be a max. So the max potential energy is also 36 joules, 0.36 joules. So that would be 1/2 kx squared equals 0.36. We'll go ahead and substitute in for the k that we got. K, where is that? There we go, 4.93 times x squared equals 0.36. So go ahead and do the math on that. And we get, actually, why don't I go ahead and do the algebra. So we'll multiply both sides by 2. So we go 2 times 0.36, right? That's going to cancel out the 1/2. And then we'll divide by 4.93. So x squared equals that. And then we'll go ahead and square root both sides. So when I multiply this out, I get 0.146 equal to x squared. And then x squared, square root both sides. And you get square root of 0.146. Go ahead and do that. Square root of 0.146 gives me 0.382 meters. So that would be our amplitude. That's our x maximum there. All right, so letter D. This one's asking for the velocity after 7 seconds. Now there actually is an equation that'll tell us the answer to this, but I'm not going to do it that way, even though it's easier, because honestly on the AP test they will not be giving you that equation. The equation they will give you is this one, x equals a cosine 2 pi ft. So they'll give you this one. This will help you find the position at that time. So we're going to do that first, and then we'll use our position to go ahead and find the velocity. Because again, on the test, they're not going to provide you with that nice equation that'll make it nice and easy for you. So we're going to substitute in all these numbers. The time here now is 7 seconds. So sorry I didn't talk about that, but we're subbing in our amplitude right there. And we're going to sub in our frequency right there. Then we're just going to multiply this out. So this will give us our position at 7 seconds. Now this is the one time in AP Physics where you do need to be in radians mode. Usually you're in degrees mode. This time, just make sure calc's in radians mode. So I'm going to go ahead and multiply this out, and I get, so very interesting, when I sub that in, here's what I actually got on my calculator. X equals 1.146 times 10 to the negative 13 Now that is a very small number. In fact, you know what? That number is basically 0. So notice, let's just take a step back. Why is it saying 0 meters? Well, notice our period was 4 seconds, right? I'm just going to draw the graph of this. So the period saying 4 seconds. If this was like x versus time, so this is our x position, right? So we start here at the amplitude, at the max, and our graph's basically going to look like this, right? So notice here, we said the period was 4 seconds. So this is when it repeats right here at 4 seconds. But notice this, when it first comes down, this would be 1 second. This would be 2. This would be 3. And then here's our period at 4. So if we continue our curve, we're going to be at 5 seconds at 0. We're going to be 6 at the max. And then we're going to be 7 back here at 0. So they just happen to give us the perfect time that would have us back at equilibrium, right? And so our position is going to be 0. So if I would have taken a step back and, thought about it, I probably could have saved myself some time. But then again, what if they gave us like 7.8 or 7.2 or 6.3 or whatever? In that case, you would have to find this position first to solve it. So anyway, so our position is 0 meters, which means we're back at equilibrium, which means our velocity would be the same as the velocity max. So our answer is, where's my velocity max? Oh, they gave that to us. So 0.6 meters per second. All right, let's move on to the next one. All right, so this question can be confusing at first, so I'll try to go through the concept of this. So we're going to have our spring here. It's going to be vertical, and we're going to attach a mass. Now let me go over what it's not doing, but we'll do that to figure out what it is doing. So let's imagine this. Let's say we had 0.100. There's our kilogram mass here. Let's imagine I just kind of slowly let this fall down. So let's say I stick my hand here. I'm going to let it kind of like slowly slip down. We did this lab, right? We let it come down here until it just reaches this equilibrium point. Okay, so it's going to be right here at equilibrium. So we did this problem in class. So to find, let's just call this distance x, how far it would drop, well, we'll just use our kx equals mg. So our k in this case was 18. Let's solve for x, okay? So it's going to be 0.1 times 9.8. So x is going to be equal to 0.1 times 9.8 divided by 18. Gets us about 5 centimeters, 0.0544 meters. Okay? Now that's not what the problem's saying, because in here we're helping it, we're kind of doing work here, or we're doing negative work, I guess, to let it go to this point. We're actually taking away energy as we let it drop to this equilibrium point. What this problem's actually saying you're doing is not this. What you're actually doing is we're attaching our mass and we're just going to let it fall freely. So in other words, we're just going to let go of it. It's going to start falling. So this potential energy is going to start changing into kinetic energy, right? So it's going to stretch out the spring. Now when it reaches this equilibrium point that we just found, okay, of, what was it, 0.0544, well, now it has like a maximum kinetic, and then it's going to start the spring's going to start stretching beyond the equilibrium point, and it's going to slow it down and stop it. Well, guess what? It's going to stop it at exactly 0.0544 when it reaches that same distance beyond the equilibrium point. And then all that energy, all that kinetic energy here is now going to get turned into potential energy. And then it's going to just repeat and go back up to this point. So to answer this question, how far does it fall before brought to a momentary stop. It's just going to be this initial drop point to equilibrium and then the additional distance afterwards. So that distance, x total, is equal to 0.0544 times 2. So we'll just multiply by 2 and we get basically 11 centimeters, or 0.109 meters. Okay, now the frequency should be pretty easy. Frequency, we'll just use our good old t equals 2 pi square root of m over k. And we'll just substitute in there, right? 2 pi square root of mass, 0.1, divided by k of 18. Now that gets us our period, but remember, period is equal to 1 over frequency. Okay, so let me go ahead and do that. So I'm going to go 2 times pi times the square root of 0.1 divided by 18, and I get 0.468 seconds. And then we'll go ahead and reciprocate that, and I get about 2 hertz, or 2.14 hertz. All right, let's move on to the next one. All right, we have our horizontal spring again. 2 kilograms. And we are going to compress it 10 centimeters. And we're going to release. And when we release it, it's going to decompress by 5 centimeters. So actually, I mean, the way this is phrased, it's saying this is 10 centimeters. It goes 5 centimeters this way. So be careful. I mean, in this case, it's 5 centimeters. It's at the halfway point. But, you know, if they said it compressed 3 centimeters, then you would want to look at like this point right here, right? The 7 centimeter mark. But anyway, we made it easy. It's exactly at that halfway mark. And they want to know the velocity there. So the key for this is conservation of energy. So we know way back here it's all spring potential. Now as it starts moving, that spring potential is turning into kinetic. But it's not all kinetic. Right here we have both kinetic and potential energy. So when we set up our equation, we'll do our US max equals US at 5 centimeters plus KE at 5 centimeters. So 1/2 K was 105, and then 10 centimeters was 0.1. And then we're just going to repeat that, but this time we're at the 0.05 meter mark. So we have less kinetic energy, right? And that's because the rest of it gets turned into kinetic energy. So that's going to be 2 and v squared. That's what we're looking for. All right, so I think I'll just do this out just so you can see the algebra. So we got 0.5 times 105 times 0.1 squared. That gets me 0.525 joules. That's how much potential energy I started with. 0.5 times 105 times 0.05 squared. So notice at this point I only have 0.131 joules plus this. So we have less energy, right? And that's because the rest of it gets turned into kinetic energy. In fact, 0.525 minus that answer we just got means we have about 0.394 joules of kinetic energy. Okay, and then we can just solve for that. 1/2 times 2, oh, that's nice. So we'll just go ahead and square root that. Square root of 0.394, and that gets me 0.627 meters per second. Okay, what's the max velocity? Well, that's fairly easy, right? The the max velocity happens when we go back to equilibrium, so like right here. So that means all that potential energy, 0.525 joules, all of that gets turned into kinetic energy. So relatively speaking, that's fairly easy compared to that one we just did. So we'd say like all the kinetic energy max is equal to all the spring potential max, which we just calculated out to be 0.525. So that should be 1/2 times m times v squared. So we'll just go ahead and square root that, and 0.525, I already have the answer there, but I'll just double check in the calculator, and sure enough, yeah, I get 0.725 meters per second. All right, moving right along. All right, let's look at this question. This is actually a gorgeous question here because it utilizes multiple concepts. So basically in this one, we have a 4 kilogram block moving at 8 meters per second, and it's going to collide and stick to a second block. So this is kind of the before, looks like this. And then the after, this 4 sticks with this 4, and then they move off like here. So 4 and 4. So let's go over actually what not to do. What you don't want to do is basically say the kinetic here, this kinetic at this point gets turned into spring potential over here. And the reason you don't want to do that is this 4 kilograms is going to stick here. When it collides and sticks, this is called a completely inelastic collision. When that happens, we're going to lose some energy. So you can't just say the kinetic equals potential because we lose some energy right here. So the way you want to solve this is you want to use conservation of momentum. So P initial equals P final. And from there, you can get the actual velocity after it collides and sticks. And then you can use kinetic, gets turned into spring potential. So that's how you want to approach it. Now, as it turns out, I gave you really easy numbers here because, I don't know why I did, just to make it easy, I suppose. So let's just do you should be able to do this one in your head. If it's going 8 meters per second, and since the masses are equal, then when they collide and stick, that means they should now be moving with a velocity of half, exactly half. Okay, if you don't believe me, you can solve it. mv equals m plus mv. So when you do that, you get mv equals 2 mv. And you can see that this is the v after, right? You can see v after is equal to 1/2 of v before. So anyway, this is how you'd have to solve it if they gave you weird numbers. In other words, if the masses were different. But they didn't, so we know it's going to be 4 meters per second. All right, so anyways, now we'll do kinetic equals potential. So this will be 1/2 mv squared equals 1/2 kx squared. That's how we're going to get the amplitude. We can cancel these halves here. Now just remember to use the 8 here for the mass. And just remember to use the new velocity, not the 8 meters per second, but the new velocity, which is 4 squared. And then our k was 160 times x squared. All right, so I'm getting 8 times 4 squared divided by 160. That gets me 0.8. 0.8 equals x squared. Square root that. 0.8 square rooted, and I get 0.89 for x. So that's right here. X equals 0.89 meters. Okay, and then the period. All right. At this point, you should be able to do this with one brain tied behind your back. So t equals 2 pi square root m over k. And again, just make sure you use 8 for the mass. And then we'll just divide by 160. All right, and what do we get? 2 times pi square root of 8 divided by 160. And I get 1.4 seconds. Great. Let's move on to the next one. All right, this looks like it's going to be a somewhat long-ish problem. So we have our mass again. This is 0.3 kilograms. And we're going to pull it back 30 centimeters. It's going to start oscillating in SHM. The period is 3 seconds. So let's go ahead and solve for things. So t equals 2 pi square root of m over k. Okay, at this point I feel like I've done the algebra for you, so you can flip back and watch the other parts of this video to solve for this, watch the algebra. I'm just going to go ahead and solve it here. So I get a k of 1.32 newtons per meter. Okay, the frequency. Frequency is inverse of the period. So we'll just inverse our period. So that should just be 1/3 hertz. Okay, let's find the displacement. So we got to look at the displacement at 0.3 seconds, right? I almost just blindly did the total amplitude. We're going to find the displacement at that certain time. So we're going to use this equation right here. And remember, this is the one time of the year where we want to make sure we're in radians mode. So this equation is given to you on your formula sheet. Now the amplitude is the 0.3. That's the 30 centimeters right here. And then we'll go cosine of 2 pi, and then we just calculated frequency of 1/3. And then the time is the time they want, so the time is at 0.3 seconds. All right, so go ahead and plug that in. Make sure you're in radians mode, and you get 0.243 meters. By the way, a quick and easy way to know that maybe you did something wrong is, remember, our total amplitude was 0.3 meters. And when we go back and forth, it should be oscillating between 0.3 and negative 0.3. So if for some reason you're getting something larger than 0.3, then you did something wrong. So just a quick check to see if you did it right. Honestly, the most common mistake is being in degrees mode, so check that. All right, spring potential. So we're looking for the spring potential at 0.3. To do that, we use our US equals 1/2 kx squared. And we'll use the x that we just found, actually the k also that we just found. 1.32 times 0.243 squared. So we're just going to plug that into our equation. So 0.5 times 1.32 times 0.243 squared means we get a spring potential, not very much, 0.0390 joules. Okay, A, B, C, D, E. We're looking for the kinetic. Okay, so we're basically looking at this time here. You change my color. We're looking for this time right here, right? So we have spring potential and kinetic energy. Well, the amount of spring potential we just calculated. To find the amount of kinetic, we're going to say, well, we want the energy total, right? That's going to be our spring potential plus kinetic that we just, the spring potential we just found. So to find E total, we can use the maximum. Remember, US max is going to be our E total. So for that, we'll go 1/2 kx squared, 1.32, and then we'll use the maximum x, which is 0.3 squared. So I get a maximum of 0.0594 joules. All right, and so again, some of that gets turned into spring potential, some of it gets turned into kinetic. So we just found the amount of spring potential. So we'll say our E total, let's do it right here actually. So our E total, we just got 0.0594. And our maximum spring potential, we just got to be 0.039. So whatever's left over is our kinetic energy, right? So just go ahead and subtract that out. So 0.0594 minus 0.039. That gets me a kinetic of 0.0204. That's how much kinetic is left over. That's joules, by the way. All right, and then to find the velocity, well, we know A, B, C, D, E, F, we're on F. To find the velocity, we know that kinetic is equal to 1/2 mv squared. So 0.0204 equals 1/2. The mass in this case is 0.3 times v squared. We can use that to find the velocity. Okay, so let's multiply 0.024 by 2 and divide by 0.3, and then we're going to square root that. And we get a velocity of 0.369 meters per second. And that would be at that point, right? Right here. That's how fast we're moving when we have both spring potential and kinetic. Okay, letter G, we're now looking for the force. Again, at the same position right here, right? So the force is equal to kx. Okay, and then we just found the x. And we just found the k. So 1.32 times 0.243. So we just use that x that we found earlier. So 1.32 times 0.243 equals a force max of 0.32 newtons. And lastly, we're going to go ahead and find the acceleration. Well, once you know that force, then you know the acceleration because F equals ma. So 0.32, what is this, h? 0.32 newtons equals our mass of 0.3 kilograms times our a. So we'll just divide, looks like it's about 1, right? 0.3, we can do that in our head. To be specific, to be exact, a is equal to 1.07 meters per second squared. All right, that was a longish problem, and I skipped a bunch of algebra too, so hope you followed along. All right, let's move on to the next one. All right, so this question, we are looking at all these graphs, simple harmonic motion. You know, we spent a whole day doing this, so I don't really feel like I can do it justice in a video, but we'll do our best. We're just going to sketch it out anyway. So position, velocity, and acceleration. So again, let's just imagine you kind of need for reference of like what's positive and what's negative, kind of like a reference point. So let's just say we pull it back here. So we're going to call our x position here kind of our positive x here. Then we're going to let it go, and then we'll call negative x this way, just so it can help us with our with our velocity graphs and our energy graphs, etc. So anyway, the position graph, this is a nice cosine curve. So this is going to look like this, right? Boom. How many periods did I say? So this would be 1 period from here to here. So 3 periods. So we're just going to continue on. There's 2 periods. And there's 3 periods. So 1, 2, 3. So notice that we started at a positive x. And we ended at didn't end, but we have a negative x down here. Just as we have in our, like the way that we started it this way. Okay, let's do the velocity one. So I'll try to do this right on top of it. So the velocity one, notice here that our velocity, we start off in the negative direction, right? Actually, we start off at 0, but it's going to head in the negative direction. So we're basically going to start off at 0, but we're going to go negative. And when x is at 0, that's when our velocity is going to be maximized. And then when x is maximized, that's when our velocity is going to be 0, right? So we'll just try to follow this along and try to keep it consistent with this graph. There we go. So anyways, you just want to kind of make sure that all these line up. We're just making a sketch anyways. Oops, this should go down here. This should be about like right there. So anyways, one is a cosine graph, one is a sine graph, and you just want to make sure that, you know, our velocity is negative at the appropriate time. Okay, what's next? Acceleration. So notice acceleration, same thing, acceleration is starting off in the negative direction. And it is maximized, but it's maximized negatively, right? And when we reach this point, acceleration is going to be 0. Then we go this way, our acceleration is now, the spring's pushing back, our acceleration is going to be positive. So we start off with negative acceleration, maximized, we go to 0, and then we have a positive acceleration, right? So basically this is going to look just like the x graph, except inverted. So it's going to be the exact inverse of the x graph. So let's try to model this as best we can. It is 0 at the same time that x is 0, but its peaks are just opposite. In other words, when it's negative, this is our negative a, this is our positive a, those are going to be opposite. Okay, all right, force. To be honest, I'm just going to draw force right on top of the acceleration, because the force, F equals ma, right? So the force, I'll just do it with like a dotted line here. The force and the acceleration are going to be the exact same graph. Okay, so this will be our force graph. Force is maximized when acceleration is maximized, and vice versa. So this is also our force, positive F and negative F. All right, let's do our energy graph. Energy graph's interesting because our energy graph actually never goes negative. You can't have negative energy here, right? Negative energy actually means energy is being removed, and we're not removing any energy at any point here. So let's just go black. So whenever, it's going to be hard to do for 3, but we'll do our best. Which one do they want us to do first? US? Okay, that's easy, because US is just, remember, US is 1/2 kx squared. So whenever x is a maximum, that's when US is going to be a maximum. And whenever negative x is a maximum, since we're squaring that, that's also going to be a maximum. Okay, so this one, let's see, we're going to go like this. And then we're going to go back up to a maximum here. All right, the last 3 I'm kind of not really modeling properly. You know what, here's what I'm going to do, just so you can see this done properly. Let's redraw the x. So our x1 looks like this, and I'm just going to do 1 period. So we're going to go, our x looks like this, okay? This is positive x, this is negative x. Okay, and then we're going to now do our US. We'll just do it for 1 period here. Okay, so this would be a maximum. And then when it goes to 0, it will be 0. And then it's going to go back up to a maximum. And then when it's a 0, it's going to be a 0. Then it's going to go back up to a maximum like this. Okay, so notice here when you look at this, it looks, so this is our US, this is 0. So I don't know why I did that. There's no such thing as negative US. So let's go ahead and erase that a little bit as such. All right, so yeah, so again, this is maximized when x is maximized. this is 0. And then again, when x is maximized, this time in the negative direction, that's when you have a positive US here, right? And then this would be 0 again, and then this would be here, maximized. So that would be for one period. Notice it looks like there's 2 periods in one period, and that's because, again, the negative x is going to be maximized twice, right? Or US is going to be maximized twice. Once when it's at the full positive x, and once when it's at negative x. Okay, and then kinetic energy, once you know the US, kinetic energy is pretty easy to find because it's just the opposite, right? So this would start out at 0, it would go up, maximum, down, up, and then back down to 0. So the purple, just label it this way, purple is the KE, and then the US max is the red. Okay, and then by the way, if I asked you for total energy, that graph would just look like this, a nice flat line, right? It's going to stay the same. That would be like E total looks like this. Now what about if there's friction? If there's friction, you essentially, everything just gets decreased, right? In fact, if we do the E total here, let's do E total friction. E total friction, it just looks, when there's friction, it's just going to start to decrease this way. And then all our graphs, they're essentially just going to be decreasing. So I'm just drawing a generic one here. You can go ahead and draw it in on all of them, but they're just all going to be decreasing like that. All right, let's move on to the next one. All right, this is the final question. So we have our pendulum bob, 2 kilograms. We're bringing it back 10 degrees. It's obviously not to scale. We're going to release it. We're going to find some things. Okay, the first thing we're finding is a period and frequency. So we've done this a bunch of times. So let's just whip this out real quick. So T equals 2 pi square root of L over G. So this is going to be 2 pi square root of the length, which was 2 over 9.8. So our period equals 2.84 seconds. Okay, and then the frequency is 1 over the period. So if we take the inverse of that, reciprocal, we get 0.352 hertz. Okay, letter B is now saying what's the maximum velocity. So for this one, we're going to have to first do some geometry and then do some kinetic energy. So again, the concept of this is, notice here we pull it back, so we now have some spring potential energy, gravitational potential energy, and then when we let it go, that's going to turn into kinetic energy. So the first thing we have to do is find out how high it starts from its, from the bottom point, from the lowest point here. So we'll do some geometry. So imagine if we draw a triangle like this, right? This is the length of our string, which is 2 meters. Now notice when we go all the way down here, that length would also be 2 meters all the way down. But what we can find here is this length right here. So we can find this distance by just using, what's that, our cosine? So if we go 2 cosine of 10 degrees, that'll get us this distance right there. So that's not very much. 2 cosine of 10, actually, sorry, it is a lot, isn't it? Oops, I'm still in radians mode from a previous problem. So make sure you're back in degrees mode. So we're going to go 2 cosine of 10, 1.97. Wow, it's not much at all. So that means the height here, we'll just subtract 2 from 0.197. So it's going to be 0.03 meters. Okay, so then when we do our UG equals KE, we'll just go MGH equals 1/2 MV squared. And then for H, we're just going to use that 0.03 meters. Okay, let's solve for V. Need some more space here. So 9.8 times 0.03 times 2. Then we'll go ahead and square root that. And we get a V equal to 0.767 meters per second. All right, what's the tension in the spring? All right, honestly, guys, this is a concept we haven't learned yet. But if you come back to this video, or if in a future year I teach the sequence different, then you would know how to do it. But for now, I'm just going to do it so it's in the video in case I change the sequence in the future. So at the bottom, we have mg, and we have tension. Now, if you've learned this yet, you know that this tension has to be bigger than mg because, well, it's going down and then it's going up. So the string has to pull up on this to keep it moving in the circle. So the way we do this is we go T minus mg equals ma. But this is the special A we call centripetal A. And the equation for that is mv squared over r. Or the equation for A is v squared over r. But then we'll multiply by the mass. So anyways, if you've learned this, then you know how to do this. If we haven't learned this, then, well, we're doing it now. But like I said, maybe you come back to this problem, try it later, and you're able to solve it. So this would be mv squared over r plus mg. All right, and then let's just go sub in everything and find our tension. So we're going to go m2, the v we just found, 0.767. We'll square that. We'll divide by the radius. The radius is just the string length, okay? Imagine this was a circle. Then this length of string would be equal to the radius of that circle, plus m is 2, g is 9.8. Okay, so the tension is going to be 19.6. This would be 19.6. Now notice it's going to be greater than that. As we talked about earlier, this tension has to be greater than mg. So 19 plus 0.6 plus this, which I get as 0.5776. So the tension is 20.2 newtons. All right, that concludes this long video. Please let me know if you have any questions. And yeah, I'll see you soon. Bye-bye.